We're beginning here by looking at the motion problems. So the first problem we're going to work with deals with dropping an object from a 64-foot building. All right, and so we have a function that represents the height of the object in foot, it says. All right, that should say in feet after t seconds. So I want you to think sort of common sense wise. If you were to drop an object from a tall building, okay, as it falls, is it going to pick up speed as it falls, or is it going to slow down as it falls? Or does it fall at a constant rate? For example, if I graph the path of an object as it falls, if it's falling at a constant rate, the path would look like that, right? Because anything with a constant rate would be a linear function. So is that the model that I'm going to get, right? And you can probably just look at this equation and say, okay, wait, it's not linear. Okay, so the objects, when we drop them, they don't fall at a constant rate. All right, so then is it slowing down, right? If something's not constant, then it's either picking up speed or it's losing speed, right? If it's not constant. So which is it? All right, so think about that kind of common sense wise for a few minutes. Also, when we were on linear functions, I hope I really beat into your brain the importance of understanding your variables. Okay, so I would often joke with students that they just sort of randomly plug in for a variable and hope for the best. All right, because if there's only two variables, you have a 50-50 chance of plugging in correctly. All right, but what's so important is understanding what those variables mean. All right, so if I write let statements, let t equal the time in seconds. So again, units are important, right? There's a big difference between seconds, minutes, hours, days. Okay, so we've got t being time in seconds, and then s of t. All right, so s represents, I'll put it over here. S represents the height, right? The height of the object in feet, okay? And so S of t, that means that the height is a function of time, right? The height depends on how much time has elapsed, okay? So first question, how long does it take for the object to hit the ground? So I have kind of a sad looking drawing over here of my function. All right, so this is what it looks like. And so this is the S axis over here, right? And that represents the height, and then the T axis represents time. And so I start here at a height of 64, right? So I drop it off the building, and then this is the height. Okay, it's falling straight down, right? Don't confuse this arc with the path of the object. The object itself falls straight down, but this is modeling the height of the object, right? Rather than the path that the object actually takes, which is a straight downward path. So anyway, hits the ground, right? What's the height at the ground, right? So what I'm looking for is I'm looking for the time at which the object hits the ground. So I'm looking for this value of t right here. Well, what's the height, right? And the height would be 0, okay? So I could either use my graphing calculator to find the x-intercept, right? Because in the graphing calculator, we'd have to put in x and y rather than t and s. Or if I were going to do this algebraically, so we're going to use a combination of doing things algebraically and then doing things using technology. So I would want to put in a 0 for s of t, the height. And I'm actually, in order to solve this, I am going to factor out of each term -16. Okay, if I factor that out, then I'm left with t squared. I factored out a negative, so I will get a negative, t squared minus 4, right? Some of you wouldn't do this. I bet a lot of you would subtract 64 from both sides and then divide both sides by -16, right? And you'd end up with this. When I take the square root of both sides, because I'm solving by factoring, because that's, I don't know, that's more kind of proper mathematics to solve by factoring. So this would factor into t minus 2, t plus 2, right? This helps me see that there are two solutions, plus and minus 2. But of course we would reject, right? Because how can time be negative, right? So we would reject the negative solution, and we would recognize that it takes 2 seconds, right, for the object to hit the ground. Okay, so the solution of negative 2 is rejected. So this is 2. Okay, then we are asked when is the object 20 feet above the ground? Okay, so if I were doing this algebraically, where would the 20 go? Okay, would I put the 20 in for t, or would I put the 20 in for s of t? Right, and so this is where I joke with students that they will just sort of randomly plug it. Okay, but since this is the height, right, I hope what you're recognizing is, so here's t equals 20. I hope what you, or not t equals 20, I'm sorry, height equals 20. Height equals 20 feet. So s equals 20. So you would, if you were doing this algebraically, you'd put the 20 over here, and then you would solve. Let's use technology to solve this instead of doing this algebraically. Okay, so how can I, because what I'm looking for then is I'm looking for this value of t right here. Okay, depending on how accurately I drew my picture, it sort of looks like I'm expecting a value kind of close to 2. That might depend on how well I drew my picture. So I could solve this algebraically, or I could go to my graphing calculator. So I already put mine in. So grab your calculator and enter the equation. So I entered the equation, and then for window, I went 0 to 2, okay? Because after 2 seconds, my object is sitting on the ground and I'm not interested in the path. And then I could have done a zoom fit, but I knew that my height would go up to 64 and down to 0. And so I used 0 to 70, right, as my Y min and Y max. So that represents my height. And now what I'm going to do then, well, first of all, if I look at this, so remember one of the questions that I asked you is the object slowing down or speeding up, right? Your common sense would probably have something to say about that. But look at what the graph shows, right? How could I look at a graph and tell if it's speeding up or slowing down, right? How could I tell just looking at the graph? Okay, so think about that for a few minutes, right? Looking at the graph, how do you tell where it's going faster versus slower? Looking at this curve, okay? Because remember, we talked a lot with coronavirus, we talk all the time about flattening the curve, right? We want a flat curve because a flat curve means slow growth, right? When the curve is not flat, we don't like that, right? That's showing like exponential growth. Right, when the curve is steep rather than flat. So anyway, let me go back to the y equals. So we want to know when y equals 20. All right, so I could just graph the line y equals 20. Look at this graphically, and then I've got that wonderful feature on my calculator, which if I go to second calculate and I select intersect, right? So instead of solving this algebraically, I can, wait, is that right? 1.65, why did it take me? Oh, I know why. Usually I have to mark off. I was confused for a minute because usually it would tell me to mark the left bound and right bound of the intersection point. However, because this graph only has one intersection point, it just jumped right to it. So I was confused for a minute why I wasn't doing left bound and right bound, but that's why. So anyway, we see here the y value is 20, and that happens at approximately, let's call that 1.66 seconds. All right, so next we are looking at okay, so the time here was 1.66. Okay, so next question asks me to find the average velocity of an object during its first second in motion. Okay, so we have a graph which is looking at time traveled and comparing that to height. So if I asked you just for like a common sense definition of velocity, right? Don't try to get too scientific or mathematical, just common sense definition of velocity, right? Or speed, right? Like what does it mean to be in your car and you're going 60? Okay, what does that really mean? Okay, and so velocity, and there is a difference between velocity and speed. If any of you have taken physics ever, you would know that velocity has both direction and magnitude, where speed has only magnitude. Okay, don't panic if that doesn't mean anything to you yet. But anyway, velocity or speed, a common sense definition of that, velocity is a rate, okay, or speed. You know, you go, if you're going 60, we say, oh, I'm going 60, you're going 60 miles per hour. So any rate has a unit of distance per unit of time, okay? So velocity is a rate. So it's the amount of distance we cover per the time it took us to cover that distance, right? So the amount of distance we cover compared to the time it took us to go that distance. Okay, and that's how we find velocity. This is supposed to be a fraction. Okay, so when you're going 60 miles per hour, it takes you a total of 1 hour to cover a distance of 60 miles. Okay, so we are looking at the average velocity from 1 second to 2 seconds. So what we have to figure out is we have to figure out the distance that we covered, right? The amount of distance we covered from 1 second to 2 seconds, and then compare that to the amount of time it took us to go that distance. And a symbol for average velocity is sometimes we write it with this like fancy V, like we write it like this, like V average, to show that it's average velocity. Okay, because at 0 seconds, I have an instantaneous velocity. At 1 second, I have an instantaneous velocity that's different. But I'm looking at the average in between those 2 seconds, or that 1 second. Okay, so what I want to do now, let's actually go back to the calculator. And let's go to table and look at this. And I think when I go to table set, I think I'm going to set my table, start at 0 and maybe go by like quarters. Okay, and remember that this is my height, right? And I had asked you, where am I traveling the fastest? Where am I traveling the slowest? Right, so look at the first quarter second, I move 1 foot. The next quarter second, I move 3 feet. The The next quarter of a second, I move 5 feet, then 7, then 8, and so on. So I am speeding up throughout the path. And I hope you recognize that because the graph got steeper as I moved closer to 2 rather than flatter, which at the beginning, right, the curve looked pretty flat, right at the initial part of that curve. So anyway, from 0 to 1 second, how much did I move, right? From 0 to 1 second, I went from 64 to 48. Okay, so this is going to sort of be a pain. You're going to have to bear with me as I go back and forth between the paper and the calculator. But what I really did, what I really did then, looking at this as a formula, all right, so I did this kind of common sense wise because I love starting with just doing things common sense wise. But then what does the formula say, right? And the formula is saying find S of 1, right? That's the height. S of 1 is the height at 1 second. Subtract S of 0 and then divide by like 1 minus 0, 1 second. Okay, so at 1 second, I had a height of 48. And at 0, I had a height of 64. So I moved a total of 16 feet in 1 second. Notice it's negative. The reason I get a negative velocity is because the object is falling. Okay, and again, don't panic if you know, we haven't talked about this yet, you know, as far as positive versus negative velocity. And this is something you will learn more about in Calc 1. Okay, so don't panic if, you know, I'm talking a little bit about some things that you feel like you don't have enough knowledge of yet. Okay, so I get 16 feet per, I don't know why I wrote it like that. I'm actually, if I wrote the slash, then I don't need the word per, right? So I could write negative 16 feet per second, or I could just write feet and then slash second. Okay. Now, if I wanted to, let's see, compare this to the average velocity of the object from 1 to 2 seconds. Okay. So again, writing the formula, the average velocity from 1 to 2 seconds. And again, we can use our common sense while we also plug into the formula. We would look at the height at 2 seconds, right? How much did we move from 2 seconds to 1 second? Okay, so we're going like this. Okay, so let's go back to the table. And, you know, I could always just be plugging these into the equation, but that's the nice thing about table is it gives me all my functional values and I don't have to do any work as far as plugging in. I just look at them on the table. So at 1 second, we already knew I was at 48 feet. At 2 seconds, I am at 0 feet. Okay, so that's a pretty easy computation to make, right? I moved 48 feet in 1 second. Okay, so I can see I already knew my object was speeding up, and certainly what I just found here mathematically supports that. So S of 2 is 0, S of 1 is 48. I did this in 1 second, so that is negative 48 feet per second. Okay, so I am speeding up. Now, let's say I want to know the velocity when I actually hit the ground, right? How am I supposed to figure that out? And I have this formula here. If I want to know the velocity between 2 points, the average velocity between 2 points. okay? And my point is the values of time are A and B. Okay, so time equals A, time equals B. I want to find the average velocity between those 2 points. What I'm doing is I'm just computing the slope, right? Right, the difference between the functional values. And actually, I'm writing this in terms of F, okay? But, you know, in this case, I called Fs, right? So what I've got here, right, but this is my Y value, functional values, we know our Y values. This is just change in Y over change in X, right? Because what did Y stand for? Y stood for my position, so change in position, and then the X value was time, right? So the change in position or height compared to the change in time, okay? That's how I find the average velocity. So I have to have 2 points, right? How can I find velocity at the point 2, 0? Okay, so that is where I am hitting the ground. Let's see, where is it? Estimate the velocity of the object when it hits the ground. So I hit the ground at the point 2, 0. Okay. I found the average velocity between 1 second and 2 seconds. So that would give me a decent estimate for the velocity as the object hits the ground, but a lot can happen in 1 second, right? I mean, this entire path is only 2 seconds. So a lot happens in 1 second. So what I want to do is pick another point because I need 2 points to be able to plug in to the average velocity formula, right? Because that's just slope. I can't find the slope unless I have 2 points. So how do I pick a second point, right? I want to pick a point close to the point 2, 0, right? And what's a point? What's close? I mean, that's a very subjective term, right? What does it mean to be close? Like if I picked 1.75 and then F of 1.75, which I could find that on my table because I counted by quarters, that would be close, right? That would give me a decent estimate. Again, that's a quarter of a second. A lot can happen in a quarter of a second. Okay, so what's a value that's really close to 2? And like I said, that's a subjective term. Okay, but could someone get closer to 2 than 1.75? Right, and if we were in class, somebody would raise their hand and say, yeah, how about 1.9? And then I'd say, well, who can get closer than 1.9? Can someone get closer to 2 than 1.9? And someone would say, well, 1.99. Well, what about 1.9999, right? And this should remind you of our talk about limits, right? Because then we could say, well, how close to 2 can I get, right? I can just keep adding more and more and more 9s. So if I want to pick a point really close to 2, you know, what does it mean to be really close? Again, that's very subjective, but I could pick something like 1.9999. All right, that could be my second point. And then I'd have to find the functional value. Okay, so I'd have to find S of 1.999 by plugging in. And I would be doing then negative 64 times 1.999 squared plus 64. And then I get 2, 0. Okay, so when I put that on my calculator, right, when I type that into my calculator, so I do get, and I want, you know, don't round off too quickly. Take all those decimal values. So 0.606 0.3984. Okay, so that's what goes in here. Okay, and then I'm going to use my formula. Okay, so I have this. Come back to the formula, which is, I wrote over here. Okay, so I'm going to be finding the average velocity by plugging in, finding, actually, I'll call it S. S, that's an S. S of S of 2 minus S of, that's an S, sorry, it's hard to do these. S of 1.999 over 2 minus 1.999. Okay, so what do I get? Okay, and when I subtract these, well, this is 0, so that was pretty easy. And so 0 minus that decimal I gave you on the other page was this. And so again, I'm getting negative because it's falling. And when I subtract these, I get 0.001. And I hope you know not to use your calculator for this, right? Because I could multiply top and bottom to get 1 in the denominator. 1, 2, 3 places I want to move my decimal point, right? So what I'm really doing is I'm multiplying top and bottom by 100. Right? I mean, using your calculator is fine, but if I move my decimal 3 places here, I move my decimal 1, 2, 3, and I get 63.98, which some of you would say, that's pretty close to 64. Should we call it 64? And it's negative because we're falling, feet per second. Okay, so if I want you to find the velocity at a point, right? Rather than what we were doing up here, average velocity between 2 points, right? I really wanted to know on this example, what was happening right at the point 2, 0, okay? What I did, since my velocity formula requires me to use 2 points, is I just picked a point that was really, 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 really close to the point that I was actually interested in. Okay, and so if this is reminding you of limits, that's great, because eventually we're going to learn how to find not an average velocity, but an instantaneous velocity. And that's going to involve limits. All right, so let's stop now and take a break.